Today we're going to look at something called the chain rule. The chain rule allows us to find derivatives of functions which are composite functions. The careless calculus student would look at this problem and say, well, I have this exponent here, I'm just going to bring it down and subtract 1 and then also take the derivative of what is in the inside. You can see that this is underneath my word that says wrong. That means this is not how we do it. So until we have a special rule, one way to think about doing this problem would be simply to square our binomial and take the derivative of the polynomial that remains. But not every problem can be worked out as nicely as this when we have composite functions. So let's let our composite function be h is g of f of x, where the inside function is x cubed plus 1, and the outside function is the function that squares. So a nice way to do this is to take the derivative of the outside rule, which is something squared, times the derivative of the inside rule. Now that would mean the 2 comes down and leaves an exponent of 1. Notice that the inside has not changed, times the derivative of the inside. Notice that when we do this, we do actually get what we started out with when we did this the other way. So this is the chain rule. The chain rule deals with composite functions. This would be functions embedded in other functions. Without the chain rule, we're very limited. We can only work functions like this. But with the chain rule, I can have one type of function inside of another, like here is x squared minus 5, a quadratic function, buried inside of the square root function. Here we have 3x, a linear function, inside of cosine, and so forth. So the chain rule is the derivative of f of g of x is f prime of g of x times g prime of x. In other words, the derivative of the outside of the function with the inside function not changed times the derivative of the inside function. Other notations that we'll use is dy dx is dy du times du dx, where y is a function of u and u is a function of x. Sometimes we will let du dx also be represented by u prime. Now at this time, I'm going to pause the video and let you write everything down you see on this page so you can listen well to the explanations. We're going to find the derivative of y, which is the sine of 3x plus 5, without something called U-substitution. So y prime would be derivative of sine is cosine. Notice that we do not change the inside function, times the derivative with respect to x of the inside function, which happens to be 3. And we're going to bring that down, 3 cosine of 3x. Now let's look at tangent of 5x squared. The outside function is tangent, the inside function is 5x squared. So the outside derivative is secant squared of 5x squared times the derivative of the inside, which is the derivative of 5x squared, which is 10x. Again, we're going to clean it up. Y equals the sine of x squared plus x. Y prime is the outside derivative of sine is cosine of x squared plus x times the derivative of the inside, and again, clean it up. Example 4, my outside function is raising something to the 5th power. My inside is this quadratic function. So dy dx is the 5 comes down, leaves the exponent of 4, our power rule. It is on the 4x squared plus 5, that does not change, times the derivative of the inside part, which would give us 8x. Now, there are times where we can make our problems much easier for us if we use U-substitution. U-substitution makes something that looks complicated look a lot easier. You just have to figure out what your U is. And your U is usually your inside function. So let us let this problem be reworked in terms of U. If we let our u be this inside function, then u is a function of x, and so the derivative of u would be with respect to x, and that would be 3. And substituting u in for 3x plus 5, I would have y equals to the sine of u. Now, let's find our derivative. The derivative of my outside function is cosine. So cosine of u times the derivative of that inside function du dx, which is 3. And I get the same answer. And I can then substitute back in what our u was. All right, let's look at number 2. Again, our inside function for 2 was 5x squared. Our outside function was tangent. So the derivative with respect to x of 5x squared is 10x. So here we go. Y is tangent of u. Y prime is derivative of the outside is secant squared of u times du dx. There's our 10x, and it simplifies. Now let's look at number 3. Number 3, what we need to do is determine what our u is. Our inside function is x squared plus x, so that is our u. And our outside function is sine. So y equals sine of x squared plus x becomes y equals sine of u. Now, just as a quick thing, let's take the derivative of our u. Our du dx, also known as u prime, would be 2x plus 1. And here we go. Y prime equals the derivative of sine is cosine, u, times u prime. Chain rule, times u prime. And our u prime was this. Make sure it's in parentheses, and you can bring it down to the front just to make it look a little better. Let's look at number 4. Our u is the inside function, 4x squared plus 5, du dx, or our u prime would be 8x. So again, look how much nicer our function looks in terms of u. That's u to the 5th. So y is u to the 5th. So y prime is 5u to the 4th times u prime. 5, there's my u to the 4th times u prime. Clean it up. The chain rule is really a nice rule, and it lets us work problems that are very difficult. And using U-substitution allows us to take a function that looks really, really complicated and make it look easier so we don't get hung up on what we're actually doing. So with the chain rule, our general power rule is to bring the n down times u of x to the n minus 1, and then the derivative of u with respect to x. So we're going to continue with our examples. I'm going to pause the video and let you write down everything you see on the page so that you can then listen to the instruction. So f of x equals 4x minus 3x cubed to the negative 2. Again, our u is going to be what is the inside function, and our outside function is the negative 2 power. So here's our u, 4x minus 3x cubed. Our u prime is derivative of that, 4 minus 9x squared. We could also call that du dx. And our function, f of x, is now u to the negative 2. Well, what's the derivative of u to the negative 2? It is negative 2u to the negative 3, but remember that u is a function of x, so times u prime. So f prime of x is negative 2, u to the negative 3 times u prime. Substitute everything back in, clean it up. That negative exponent means to come down here. Let's look at the next example. We have f of x equals negative 4 over 2x minus 5 to the second. We're going to rewrite that as an exponent. We're going to take our u as 2x minus 5. So looking at that, our u prime is 2. So I have the information I need. F of u is negative 4 u to the negative 2. F prime of u is therefore negative 4. That's my constant multiple. The derivative of u to the negative 2 is negative 2u to the negative 3 times u prime. So now we can substitute back in. Negative 4 times negative 2. My u was 2x minus 5 to the negative third times the derivative of u, which was 2, and clean it all up. When we have radicals in our function, This becomes algebraically a lot more work for us. So let's look at this one here. F of x equals x cubed times 2 minus 3x squared, the square root of that. First of all, we have a product. So if I think of f as, I don't want to call it f times g because f is actually my function, so we'll call it h times g, and this is a product, and our product rule would say f prime of x is hg prime plus gh prime. So h is x cubed, g prime, I'm going to take the derivative of this, we're going to have to use chain rule there, plus g times the derivative with respect to x of h. So this looks pretty terrible, but it's not so terrible. So I have x cubed, the derivative of this, notice my outside function is 1/2, so 1/2 is going to come down as my coefficient. Subtracting 1 from 1/2 leaves negative 1/2. Don't change the inside, times the derivative of the inside. There's your chain rule piece right there. Plus g times the derivative with respect to x of x cubed. Now, this is where this gets tricky, and we have aloha. Notice that in both terms, this one and this one, we have the factor of 2 minus 3x squared to a power. I have it right here, and I have it right here. When you learned how to factor long ago, you knew that when you had a factor in two terms, you took out the smaller exponent. In other words, if you had x plus 3 quantity squared plus x plus 3 to the 5th, you would take out of there x plus 3 quantity squared, and that would leave 1 here, and subtract 2 from this, and that would leave x plus 3 to the 3rd. Now, you learned that in algebra a long time ago, so that's all we're going to do, but it looks a lot uglier because we're dealing with fractions. So we're going to clean this up, and I can see that we have to the negative 1/2 here and to the 1/2. So we are going to take out in both terms what is common to both, a negative 3x to the 2nd and 2 minus 3x squared to the negative 1/2. Now, this is our greatest common factor. It's going to go right here, times. Now, look at the first term. When we take this out of the first term, factor it out of it, the only thing that's left is an x squared. Now we're going to factor a negative out of this positive, which is going to leave a negative. And notice that all of the 3x squared is going to come out, so that kind of leaves a 1 there. And what did we do with the exponents? Back here, remember, we took the 5, subtract the 2, left the 3. We're going to do the same thing. Take the 1/2, subtract the negative 1/2, and it leaves 1. 1/2 minus negative 1/2 leaves 1. And now we're going to clean everything up. This is going to stay on top. This has a negative exponent, and it is going to go down below. And on top here is x squared, and we're going to go ahead, since that's to the first power, we're just going to distribute that negative 1. And we see that we can add some terms together, and that is how we end up with our final nice answer. Notice we have a common factor of 2 here. We can factor it out and leaves out. You want to be able to simplify that much all the way. So there's a lot of algebra hidden in the work you're going to be doing. I'm going to pause to let you write down the notes that you see. All right, here we go. First step is to rewrite that radical. Notice we're going to have a quotient when we take the derivative, and we have chain rule. If you wanted to, you could write this as a product. You still are going to have chain rule with that, but just as easy to write this as a quotient and use it that way. Here we go. Low times the derivative of high minus high times the derivative of low over low, low. So what we notice is the derivative of x is 1. And now we're going to take the derivative of 1/3 power on x squared plus 4, which is 1/3. X squared plus 4 to the subtracting 1 from 1/3 leaves negative 2/3 times the derivative of the inside. Notice the derivative of the outside is this piece. The derivative of the inside is that piece. We have a lot of algebra cleanup to do. Notice that in both terms we have an x squared plus 4th, and you take the lower power, so negative 2/3. And we also have something that's kind of strange. We're going to factor this fractional coefficient out. So that means we're going to be taking 1 and dividing by 1/3. And let's remember 1 divided by 1/3 is simply 1 times 3, so that's 3. So we're going to get a 3 right here. And that's where that's going to come from. Here we go. Greatest common factor is 1/3 x squared plus 4 to the negative 2/3. That is coming out. When we factor that out of this term, guess what? 1/3 going into 1, or 1 divided by 1/3 is 3. Now, notice that we subtracted a negative 2/3 from that exponent. 1/3, when we divide out the negative 2/3, we subtract the exponents, and that leaves 1. That's nice and pretty. All of that factor is gone here in the second term, and we're left with 2x and the x that's here, so 2x squared. Notice that my 1/3 here is 1/3. I have a single fraction. This x squared plus 4 to the negative 2/3 comes down. I have 2/3 down here, so notice we're going to add the 2/3 that this becomes when we move it down to the denominator, plus that 2/3 is going to give me 4/3. Again, fractions are our friends. On top, I'm going to go ahead and distribute the 3, and I can add similar terms. Wow. Problem 9 looks terrible, but it is so much easier if we take it and write it in terms of u. Notice that I have a quotient raised to a power. Let us let u be this inside piece. So if u is this inside piece, I'm really looking at f of x equals u squared. And therefore, f prime would be 2u times u prime. So that's super simple. So we are going to have to find u prime. Well, u prime is just a quotient rule. So low d high minus high d low over low low. Do the algebra. There's u prime. Now we're ready to go. This is our roadmap, RM, roadmap. 2 times u prime. 2 times u prime. 2 times u prime. There's my f prime of x, and clean it up. So hopefully you see the beauty of U-substitution. We can also use our chain rule and U-substitution with our trig functions. So notice that the derivative with respect to x of the sine of u is cosine of u times u prime. So we have y is cosine of x squared. My u is going to be x squared, so my u prime is 2x. Okay, so my outside derivative of cosine is negative sine of x squared. Again, don't change the inside, times the derivative of the inside, which is 2x. And we're going to clean it up, bring the 2x down in front with the negative sign. Now let's look at number 11. 11, you have more to think about because cosine squared of 3x really means cosine of 3x squared. And we actually have 3 things going on here. We have the second power, we have the cosine, and we have the very inside 3x. So our u is going to be 3x. So our u prime is 3, or du dx. So y is cosine squared of u, or cosine of u squared. Well, we have multiple chain rules going on here. We have, first of all, the exponent of 2 becomes 2 times cosine u to the first power, times the derivative of cosine is negative sine of u, times the derivative of u, 3. So we actually had 3 things going on. So the derivative of our second power, the derivative of our cosine, and the derivative of our u. If we look here, our u is going to be 3x, therefore our u prime is 3. If we rewrite this, this is sine of 3x to the fourth. So f prime is, the 4 comes down, exponent becomes a 3, leave the sine 3x in there, times derivative of sine is cosine 3x, leave the 3x in there, times 3, and clean it up. Pretty nice. The chain rule allows us to make another connection between functions when we differentiate with respect to a third variable, say time or angle measure. Guess what? That's coming up. So dy dt would be dy du times du dx times dx dt, and that is coming up. And a final problem to look at is this one. If f of theta is the sine of the cosine of 3 theta, find f prime of theta. The derivative of sine is cosine of cosine 3 theta times derivative of cosine is negative sine of 3 theta times derivative of 3 theta is 3. Boom. There it is. Again, it's like a chain reaction. You take the derivative of that piece, then that piece, then that piece. And your TPs, 3, 7, 19, 43.